Today we're gonna continue from here, from shielding effect. Last class, we were discussing the factors that can affect the atomic radius, and we discussed three factors: nuclear attraction, which is directly proportional to nuclear due to number of protons. If any atom has more number of protons, it means it would have a greater nuclear attraction towards its electrons. Nuclear attraction can also be called as nuclear charge or nuclear pull. So it has three names, and you should be familiar with all three names, right? Then the second factor that can affect the atomic radius is, of course, the number of shells. If any atom has more number of shells, then obviously its size would be bigger. And the third and the most important factor was the shielding effect. And shielding effect is basically the repulsion of the outer shell electrons by the inner shell electrons. If any atom has more number of inner shell, it will exert greater force of repulsion on its outer shell electrons. So that's why when any atom has more number of shells, it has more repulsion between its inner shell electrons, due to which the size of the atom increases. Obviously, when the electrons, they're going to repel each other, the atomic shells or the quantum shells, they will move further away from each other. And when they're going to move further away from each other, obviously they will occupy a larger space or a larger volume. That's why we say the atomic size or the atomic radius increases if any atom has more number of shells, right? So in exam, they may ask you the trend of atomic radius across the period. You should know how the atomic size of the atom changes whenever we are discussing any particular period of the periodic table. For example, if we see the periodic table, here we have the periodic table, and again, this is, let me just rotate it. Okay. If you see the periodic table, horizontal rows of a periodic table are known as periods, right? And if we see any particular period of a periodic table, let's say period 1, which has hydrogen and helium element, period 2, which has lithium, beryllium, boron, and up till neon. Period 3 is this period, which has sodium, magnesium, aluminum, silicon, phosphorus, and so on. Then this is period 4. If we see any period 2 or period 3, the atomic size must decrease. I mean, the lithium atom must have the larger size, then beryllium, then boron, then carbon, then nitrogen, then oxygen, then fluorine, then neon, right? And why is that so? Because across the period, number of shells stays same. You know what period number represents? Period number represents number of shells. So across the period, number of shells in the atom stays same. So all period 2 elements, they have 2 quantum shells. However, across the period, their number of protons increases. Lithium has 3 protons, beryllium has 4 protons, boron has 5 protons. So nuclear charge is increasing. However, shielding effect is not increasing as number of shells are not increasing. So there is an increase in inward force. That's why the electrons of these atoms will move closer towards the nucleus as their number of protons increases. So if I ask any one of you to just describe the trend, not just describe, but also explain the trend. Whenever he asks in the question to explain the trend of atomic size across the period, how would you do that? You have to talk about all the factors that can affect the atomic size. So trend of atomic radius across the period is, as we move across the period, size or atomic radius decreases across the period. Reason being because nuclear attraction increases due to increase in number of protons. But number of shells stays constant. So shielding effect stays constant. Right? Getting it? Very good, Rida. Atomic size decreases going down the period. Actually, when we go along the period, we say going across the period. Okay, down is for groups. So we are moving across the period, right? Number of protons increases, causes greater nuclear attraction. But you have to discuss the other factor as well, which is the shielding effect, which stays constant due to number of shells staying constant. Getting my point? Okay. You guys need time to write it down. I think I just couldn't share the yesterday's recording and the class notes. Okay, I will do it just right after this class. Don't worry. Yes, Rayan, Faik, and Sarah. Sarah, you were there in the last class. I think you were absent. Should we move forward? Now we have to see, okay, you need 2 minutes. Okay, Rehan. Okay, Sarah, it will become hard to catch up in today's class if you do not know what shielding effect is. Do you have idea of a shielding effect? Okay, good. Okay. Now, again, same, you have to discuss the trend of atomic radius down the group. So down the group. Sometimes they write radius as radii, and radii is basically the plural of radius. So if you see the word radii, it means it is the plural for radius. Okay, it's the same thing. Now down the groups, the size of atom increases, right? And why the size of atom increases? Because as you move down the group, number of shells increases. But nuclear attraction is also increasing down the group as number of protons are also increasing. If you see lithium, sodium, potassium, if we take an example of group 1 elements, lithium has an atomic number of 3, sodium has an atomic number of 11, potassium has an atomic number of 19. So going down the group, number of protons increases, due to which nuclear attraction increases. So due to increase in nuclear attraction, there must be a decrease in size of the atom, right? Make sense? However, there is an increase in number of shells as well. When number of shells increases, this increases the shielding effect. So one of the factor is trying to increase the atomic radius. The other factor is trying to decrease the atomic radius. Down the group, as number of protons are increasing, nuclear charge is increasing. So it is trying to decrease the atomic radius down the group. But as so more number of shells means more atomic radius, greater atomic radius. Secondly, when number of shells increases, shielding effect also increases, right? So two of the factors I can say are actually contributing in increasing the atomic size. Getting my point? However, one of the factors, that is nuclear pole, is trying to decrease the atomic size. So the overall effect is these three factors, they are fighting with each other. Nuclear attraction is trying to decrease the atomic size, but increase in number of shells and increase in shielding due to increase in number of shells is trying to increase the atomic size. So shielding effect actually wins when it comes to the fight between nuclear attraction and shielding effect. So we can say that effect of shielding is more significant as compared to effect of nuclear pole. So overall effect is that the size of atomic size increases down the group. So how do you formulate this answer? Atomic size increases down the group, although means nuclear attraction is increasing, but with it, number of shells are also increasing, which increases the shielding effect. So effective nuclear attraction decreases. What does effective nuclear attraction means? The resultant force that we were talking about in last class. As nuclear attraction is increasing, but shielding is also increasing. So resultant nuclear attraction basically decreases. So in place of resultant, we use the word effective nuclear attraction in chemistry. Getting my point? So far, so good. Ryan, Faik, and Sarah. And you are still writing? I just need to put a charger. Okay, just give me a moment. Okay. Sometimes things like this happen. We still have to charge our device. I don't know when we will go to completely to the wireless technology. Okay, that's good. Okay, should we move on? Okay, if we see the graphical version of the atomic radius, we will see that the size of the atomic radius is decreasing across the period 3. This is the trend for period 3 actually. It will be same for period 2 as well. This is the trend for period 3. So from sodium to magnesium and aluminum, silicon, phosphorus, sulfur, chlorine, the atomic size is decreasing. You're not supposed to remember the sizes of these atoms, but you just have to know the trend of the atomic size across the period. If you see the trend of atomic size down the group, the atomic radius down the group increases, so the trend would be like this. If we take an example of group 1, lithium, sodium, potassium, rubidium, cesium, francium. In fact, if we take the example of group 2, again the same trend will be followed like this. If I make the trend of group 2 atomic radius on the same graph, where should I draw the curve? Below this curve or above this curve? I'm asking you guys. If I need to make the trend of atomic sizes of group 2, so should I make this curve below the curve of group 1 or above the curve of group 1? Above the curve. Okay. So do you know what if lithium is in group 1? If we're going to make the graph for group 2, so this first element of group 2 would be beryllium. So you are saying that if we're going to draw the curve above this curve, so beryllium's atomic size has to be greater than sodium. Is it the case? Across the period, atomic size decreases. So beryllium's atomic size is greater than lithium or smaller than lithium. You have to decide it. Across the period, atomic sizes decreases. Why are you saying that we have to draw the curve above this curve? Rayan and Rida, can you guys explain? We have to draw this graph below this curve because across the period, the atomic size decreases. So beryllium has to be smaller than lithium. But as we move across the period, because if we are making the graph of group 2, then in group 2, in third period, there would be magnesium, and magnesium size should be smaller than sodium. Same goes for potassium size is bigger than as compared to the its third period element, which is calcium, and so on. Right? So this is the trend for group 2, and the first one is the trend for group 1. Got it? So across the period, atomic size decreases and down the group, atomic size increases. I was expecting a question from you guys in this. I have made this trend of atomic sizes across the period. Nobody asked me one thing where you should be asking. Don't you see anything missing in this curve? Seriously. Do you guys have product tables in front of you right now? Nobody. Let me show you period 3, or in fact, if you are making the graph of period 2, so it starts from sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. Does it end at chlorine? It ends at argon. If you see the trend, have I drawn the trend including the argon atom? See this trend. Do you see the argon atom drawn? The size of the argon. In case if I have to draw it, where should I draw it? At below chlorine or above chlorine? It should be drawn below chlorine, right? The size of the argon atom should be smaller than chlorine. Then only it will make sense because we have already established the trend that atomic sizes decreases across the peak. So argon's atomic radius should be smaller than chlorine's atomic radius. But why argon is not drawn over here? Because if we measure the size of the argon atom, actually it is bigger than chlorine, and it is in fact more bigger than sodium atom. So our graph would look something like this. So the trend that we have established would be ruined. Why? Because argon's atomic size is greater than not just chlorine, but greater than sodium. And now, if we just draw this argon on the graph, then it means we have just the trend that we have discussed would become null and void. So is it argon's atomic radius actually greater than the atomic radius of sodium? No, but there is a problem measuring the radius of the argon. In fact, there is a problem measuring the radius of all the elements. It is actually not directly part of your syllabus. The specification just asked us to just show the trend from sodium to chlorine. You do not have to include argon. But out of curiosity, you should be able to notice that argon is not included in the trend. Why not? Shouldn't it follow the same trend? It should. Because if we see the number of shells in the argon atom, there are 3 shells. Same number of shells are there in the chlorine, sulfur, phosphorus, silicon, aluminum, magnesium. And the number of protons of argon atom are greater than chlorine. So its size should be smaller than chlorine. But the problem is the way we are measuring the atomic sizes is incorrect. Do you know, we consider the atoms as spherically shaped. It is a noble gas, but what it has to do being a noble gas? It has something to do with the noble gas, but what I'm saying is it is very difficult to measure the size of the atom. Do you guys recall in grade 11, you must have studied something about, in your physics paper, you must have studied something, or not just in physics, but in mathematics as well, that if we have like a few number of tennis balls placed side by side with each other. If I ask you to make, considering these all balls are of the same size, how do you measure the diameter of each ball? Either you can use your vernier caliper or micrometer. Screw gauge is basically used to measure very small radiuses. But as for the larger radiuses like the tennis ball, you cannot use the micrometer screw gauge. You have to use a vernier caliper. You know what vernier caliper is? The instrument that has jaws and it opens and anything spherical comes in between the jaws, right? Again, if the ball is larger in size that the vernier caliper cannot even measure it, then we have another method of measuring the size of these balls. In short, I'm just trying to measure the diameter of these balls. So what we used to do is we used to take set squares. You guys know what set squares are? If you guys must have always wondered, in your geometry box there are two scales or triangular shaped objects that are used to measure the diameters. Basically, what we do is we keep two set squares at both the edges of these balls. We keep, like, let's say we are keeping 5 tennis balls adjacent to each other, and at the one end we are keeping the set square, at the other end we are keeping the set square. And then we put a meter rule or a scale over these set squares, and we just simply measure the dimensions of the all 5 balls, the length of all these 5 balls. Let's say it is D. And when you're going to divide D by 5, we will get the diameter of each ball. Right? And when you're going to divide this diameter, we will get the radius of each ball. I'm not saying that you will be tested on this knowledge, but as a matter of fact, you should know, you should always try to study one step ahead. It's okay, you are not supposed to write it down, but I'm just telling you out of curiosity, if anyone has a question why argon is size which should be smaller than chlorine, but still, if I'm going to draw argon over here on this graph, it should be bigger than sodium. So the thing is, how do we actually measuring the atomic sizes? Are we using this method? The way we have measured the diameter of the tennis balls, we are sort of doing the same thing. Actually, what happens, atoms are so small that you cannot pick one atom, right? You guys know atoms are very, 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 very small. You cannot even see an atom. How do you can even pick one atom? It's not possible. And you will always deal with the large number of atoms. In order to quantify the large number of atoms, we have introduced moles. So 1 mole of any atom has Avogadro number of atoms, which is 6.02 exponent 23 atoms. Same, what we do is, if we take any object containing sodium, so sodium is a metal, we know that a piece of sodium element would have large number of sodium atoms arranged in this way. So if we measure the length of this, then we can, if we divide the by number of sodium atoms, then we will get the atomic size of each sodium atom. We cannot actually measure the atomic size. We can measure the length of large number of sodium atoms, then we can divide by the number of sodium atoms, and that's how we will get the diameter or the radius of sodium atom. But the problem is, these tennis balls could be kept edge to edge with each other. I mean, it is a boundary of this tennis ball and the other tennis ball. These boundaries won't overlap with each other, right? If I have a ball, right? If we see, if I have this one atom and the other atom, if we consider it balls, then their walls would touch with each other. They won't overlap with each other. They won't go inside each other. But the atoms are empty spaces. Atoms' outer shell is not like a boundary that it does not allow anything to come into over across this boundary. Atoms are empty spaces. So what happens if we have sodium atoms placed adjacent to each other? So part of the sodium atom, part of the outer shell will always overlap with the part of the other atom. So that's why when we're gonna measure the length of these sodium atoms, there will always be an error. See, if we measure the length of these sodium atoms and if we're gonna divide it by 2, dividing it by 2, we will get this size, which is from the center of one sodium atom towards this line. This radius will always be the incorrect radius because we are underestimating this radius. The actual radius should be up till here. The actual radius should go up till here, this point. However, when we are using this technique to measure the atomic radius, what happens that we are unable to measure the accurate or the actual radius of any atom, due to which the radius we are calculating is not the actual radius. But just to give you an idea that magnesium atomic radius would come smaller than sodium, then aluminum's atomic radius would come then magnesium, smaller than magnesium, and it will keep on decreasing. So argon's atomic radius should be also be smaller than chlorine. But the problem with argon is not bonded with other argon atoms. Sodium is bonded with the other sodium atoms through metallic bonding. Magnesium is bonded with other magnesium atom through metallic bonding. Silicon is bonded with other silicon atoms through covalent bonding. And you know, when a covalent bonding takes place, there is a larger overlap of shells or orbitals to make a covalent bond. And in this overlapping region, you always have shared pair of electrons. So sulfur again is a covalent molecule, chlorine again is a covalent molecule. So when two atoms of chlorine are adjacent to each other, they have formed a covalent bond with each other. However, in case of argon, argon is a noble gas. It does not participate in bonding. So when we have to measure the sizes of the argon atom, we try to cool it. But its freezing point is so small that we are unable to bring the argon atoms closer to each other. I mean, we cannot just cool it down to an extent that the argon atoms will come so close to each other that they start touching each other. This does not happen. If it does not happen, it means two argon atoms adjacent to each other will have a gap between them. Right? And when we measure the distance between these two argon atoms, and when we're going to divide it by 2, then we will get this radius, which is greater than the actual radius of argon. See, over here, this distance, the distance that I'm highlighting, this distance is always our overestimation. And due to this overestimation, when we actually put the radius of argon on the graph, it becomes greater than sodium. However, in actual, the radius of argon should not be greater than sodium. But due to our faulty measurement technique, then this argon's atomic radius comes greater than sodium. No, there is no metallic bond, there is no covalent bond in metals, but there is an overlap. Why there is an overlap? Because if you recall, sodium, magnesium and aluminum, they have metallic bonding. And how does metallic bonding happens? we say that metal positive ions are surrounded by sea of delocalized electrons. So when these metal positive ions are closer to each other, what happens? There is a partial overlap between their orbitals. If we have one sodium atom and the other sodium atom, and their outer shell electrons are outside their shell as a sea of delocalized electrons, what happens? They both are trying very hard to attract this sea of delocalized electrons. So due to which atoms is not a definite boundary. The outer shell of the atom is not a definite boundary. That when it comes in contact with each other, it won't stop. They may somehow partially overlap with each other. So this overlap is not due to the covalent bond, but this overlap is due to because the outer shell is not a definite boundary. So when they're going to come closer to each other, so there may be a partial overlap between each other. Yes, all the atoms. If we are dealing with covalent molecules, in a covalent molecule, atoms are covalently bonded. So there has to be a complete overlap. Complete overlap means there is a good amount of overlap to have a shared pair of electron in that overlapping region. However, in case of sodium, magnesium, aluminum, atoms are bonded to each other. They are close to each other. But there may be a partial overlap, but not a overlap less like in covalent bond. So if you see from sodium to magnesium and aluminum, the decrease in atomic size is not that great. But as you see from aluminum to silicon, you can see one steep line. And that steep line is due to because from silicon, we have a covalent bonding. So there is a greater amount of overlap between two silicon atoms. But in case of argon, there is no overlap. And in fact, argon is a gas at room temperature. If we try to cool it down, we cannot cool it down to an extent that it becomes a solid. And even if we bring the temperature to that low, again, how would we measure or perform our experiment in that cooler region? So that does not actually happen. Up till now, it is not possible to accurately measure the atomic radius of argon. Once we know the technique, then if we find out the actual radius of argon, then it should be definitely smaller than chlorine. It would be smaller than chlorine, right? But for now, as far as our specification is concerned, we're not supposed to make the atomic radius of argon on this trend. Got it? Okay. Here's this one practice question for you guys. You guys must have periodic tables in front of you to answer this. Put the following elements in order of increasing atomic radius. Justify your answer. Just put it in the order of increasing atomic radius. Justification we can do later. Magnesium, sulfur, and silicon. Which one of these has the smallest atomic radius? Magnesium, sulfur, or silicon? Magnesium. Why? Because magnesium is from period 3. Sulfur is also from period 3. Silicon is also from period 3. And we have already established across the period atomic size decreases. So the rightmost element in the period 3 must have the smallest atomic size. And the leftmost must have the largest atomic size. If we see period 3, we have sodium, magnesium, aluminum, silicon, phosphorus, and sulfur. Sulfur size should be the smallest as compared to silicon and magnesium. Got it? Rida, Rayan, 5. Which one should have the smallest size? That should be sulfur. Sulfur has the smallest size. Then comes greater than sulfur should be silicon, and this largest size must be of the magnesium ion. Rayan, Rida, Faik, and Sara. Guys, you need to confirm me. If you are unable to understand it, we can repeat it. Okay, Sarah, what about you? Sarah, would you like to answer for the question B? Okay. Just tell me the trend of increasing atomic size between these three atoms, magnesium, potassium, and aluminum. If you want, I can show you the periodic table. Here. Aluminum has the smallest size. Here is aluminum, which is in period 3. Magnesium is in period 2. Sarah, I'm expecting answers from you, please. Quick. And here we have potassium. Aluminum, magnesium, and potassium. Very good. Potassium is in period 4. It has 4 shells. Magnesium and aluminum has 3 shells. So naturally, size of the potassium should be bigger as compared to magnesium and aluminum. So the potassium must have the largest atomic radius. In between magnesium and aluminum are in the same period. So across the period, size decreases. So aluminum must have a smaller size as compared to magnesium. So magnesium has a greater size as compared to aluminum. The smaller size is that of the aluminum atom. Then we have magnesium atom, and then we have potassium atom as the largest. Okay. Ryan, now it's your turn. Bache, I need you to answer for part C, silicon, chlorine, and potassium. Ryan and Faik. For C, it should be potassium, silicon, and chlorine. Okay. See, potassium is from period 4, so it has 4 shells. Chlorine and silicon are from period 3. So the largest size should be of the potassium atom. Then in between chlorine and silicon, as they both are from period 3 and chlorine is further in the period 3, so it must have smaller size. And silicon must have a greater size as compared to chlorine. So the order should be chlorine, silicon, and potassium. Very good, Sarah, Rayan. Silicon is not the smallest. Okay, chalo. Very good. All 4 of you have answered it correctly. I'm happy that at least you guys know what the concept is all about. Let's discuss the ionic trends of down the group and across the period. So first group 1, or take an example of any other group. Let's take an example from group 1. The trend for the atomic sizes down the group increases, right? Lithium has a smaller size, cesium has the larger size. Now we are talking about down the group, right? Now if we make the trend of their ionic radii, and we know that all group 1 elements, when they form an ion, they lose 1 electron. So they are left with 1 lesser shell. Lithium atom has 2 shells. Sodium atom has 3 shells. Potassium atom has 4 shells. I cannot make the electronic configuration of, I can actually rubidium. Now I can, because in A level I know how to make the electronic configuration of all the elements. But a rubidium atom must have how many number of shells? 5 shells, because it's in period 4. Cesium must have 6 shells. If we make the lithium ion, then lithium ion is left with 2 shells, because it's gonna lose 1 of its electron from the outer shell. So now it is left with 1 shell only, because there are no electrons left in the outer shell. Sodium atom is left with 2 shells. Let me just write you the number of shells. Lithium ion is left with 1 shell, sodium ion is left with 2 shells, potassium ion is left with 3 shells. So if we compare the size of the potassium ion from its corresponding potassium atom, it has to be smaller, because potassium ion has 1 fewer shell as compared to potassium atom, right? So if we just make the trend of their ionic radius down the group, then lithium size should be smaller than sodium ion. Sodium ion should be smaller than potassium ion. But if we compare their sizes from their corresponding atoms, the size of their ion should be smaller than their respective atom. Getting it? Ryan? All okay now? So the trend below is for the ionic radius of the same group. And the trend above with the solid line is basically the atomic radius of the same group. Got it? Now, if I ask you to make the trend of group 17 down the group, you have to make the trend of radius versus group 17. Group 17 is your halogen, which is fluorine, chlorine, bromine, and iodine. If I make the trend down the group, definitely the atomic trend would be like this, where we have fluorine, chlorine, bromine, iodine. Fluorine, chlorine, bromine, and iodine. Now, if I asked you to make the trend of their ionic radius, so what do you think? That line would it be below this graph or above this graph? In case of atomic ionic trend in group 1, group 2, and group 30, it should be the ionic radius should be smaller than their corresponding atomic radius. But what about noble gases of, oh, sorry, not noble gases, what about non-metals? It will be above the graph, because when the fluorine atom forms a fluoride ion, it gains electron. It doesn't loses an electron. Fluorine atom, when it gains electron, it forms negative ion. Bromine atom, when it forms an ion, it gains electron. Iodine atom, when it forms an ion, it gains electron. So they form negatively charged ion by gaining an electron. So there is no loss of outer shell. In fact, in the outer shell, one extra electron is added, due to which slight repulsion between these electrons increases, because we have already established that the electrons of all shells, they are repelling each other, so they are trying to move away from each other. So when the extra electron is added to any atom outer shell, what happens? The repulsion increases, due to which, what do you think? The size slightly increases. Won't it be same? Yes, it should be same, because there is no change in shell, but due to the addition of extra electron, the size slightly increases. So if we see the trend of ionic radius uh, down the group 17 or any other group which gains electron to form a negatively charged ion, their size ionic trend should be like this. I mean, the fluoride ion must have a slightly bigger radius as compared to its corresponding fluorine atom. A chloride ion must have a slightly bigger ionic radius as compared to the ionic radius of the chlorine atom. A bromide ion, after gaining an electron, there is a slight increase in repulsion between the electrons, so they will move farther away from each other. So there is a slight increase in size of the bromide ion as compared to the bromine atom. So its atomic ionic size should be greater than or slightly greater than its corresponding bromine atom, and same goes for iodide. Got it? Easy, easy. Should we move on? Okay, moving on. And in next class, we will start doing our past papers. So by the next class, you all are advised to revise this chapter thoroughly. And do you guys have worksheets, any worksheets of sort topical past papers or something? Because we're gonna do the past papers from recent years first. But if you guys have other past papers or worksheet, you can start trying questions from that. Otherwise, I'll provide you with the worksheets. Okay, moving on. The next concept that we have to study is ionization energy. You guys already know what ions are, right? Whenever we have to make an ion, we actually either remove electron or gain electron. An atom, either it gains electron or it loses electron. So when we have to forcefully form an ion from the atom, we actually try to remove the electron. So ionization energy is basically the energy required to remove the electron from any atom. For example, if we have a sodium atom, its valence shell has one electron. And this valence shell is actually under the nuclear attraction of the sodium atom. But if we somehow want to remove this electron from the nucleus of sodium, from the nuclear pole of sodium atom, we have to supply it some amount of energy in the form of heat. And we're going to supply this energy. So the amount of energy that is actually required to remove this electron is known as ionization energy. And the thing is, whenever we are dealing with any atom, molecules, or ion in chemistry, we cannot actually deal with one atom, because one atom is so small that you cannot pick one atom. If I just asked you to pick one sodium atom and try to heat it with a lighter so that its valence electron just moves out of the shell. So you cannot just pick one sodium atom. So we always have to deal with a large number of sodium atom, because even if I asked you to just pick the tiniest amount of sodium element, that tiniest amount would have millions and millions of sodium atom. So the point is, we cannot deal with one sodium atom. Similarly, we couldn't deal with the sodium atoms or any element or the mass of the any element back in grade 11 as well. If we used to say that the mass of sodium is 23 grams, which is the relative atomic mass of sodium, was it the mass of one sodium atom? I'm asking you, was it the mass of one sodium atom? 23 grams. No. It was the mass of how many sodium atoms? 1 mole. Very good. But how many number of sodium atoms equals to Avogadro number? 6.022 exponent 23 atoms. Right? And we used to call it 1 mole of sodium atoms. Right? So whenever we are dealing with any sort of quantity in terms of atoms, molecules, or ions, either it is a mass or volume or number of atoms, we try to introduce a new unit which is mole. Whenever we have to deal with the mass of any element, molecular mass of any compound, or the volume of any gas, we try to start our working from 1 mole of that particular substance. Similarly, if I say I have to remove one electron, then it would be very difficult to calculate. We can calculate it, but the point is the values would be too small that it becomes very difficult to manage. So what we do is we actually try to study all the values per mole of that particular substance. So if I say I have to remove one electron from one sodium atom, that is correct, but it is very impractical to calculate or measure. So what we do is we try to find the energy that is required to remove 1 mole of electrons from 1 mole of sodium atoms, right? So we'll be dealing with 1 mole of everything. So what does ionization energy is? It is the energy required. It is the energy required to remove 1 mole of electrons. 1 mole of electrons would have Avogadro number of electrons. That's why I have put an S after electron, because it has to be a plural quantity. So it is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form. Why I am saying gaseous atoms? Because if I asked you to bring me the sodium, if I asked you, today we will going to remove the electrons from the 1 mole of sodium atoms. How would you bring me sodium? Sodium exists in the solid form. It is a metal. It exists in the solid form and room temperature. First, when we start heating sodium, what will happen? First, it will melt. It will form liquid sodium or molten sodium. Further heating sodium, it will boil the sodium to form sodium gas. Then after once all the sodium atoms are away from each other, if we continue heating, then the electrons will start getting removed from the sodium atom. So this conversion from sodium solid to liquid is melting, from liquid to gas is boiling, and the energy required to melt any object or boil any object is basically the latent heat. Latent heat of fusion or latent heat of vaporization. I'm not sure if you have already studied that back in grade 11, but these heat energies are known as latent heats that are actually required to convert the state of any object. If you need to convert solid to liquid, that is known as latent heat of fusion. If you need to convert liquid to gas, that is known as latent heat of vaporization. I'm not sure if you have already studied that or not back in your grade 11 in physics, but let's say if you haven't studied it, for now, ionization energy is basically the energy required to remove the electrons from gaseous atom. What we are calculating is we are just trying to calculate the energy that is required to remove the electron from the gaseous atom. Why? Because obviously the sodium element would be given in the solid state. But all the energies that are required to bring sodium from solid state to gaseous state are not included in the ionization energy. Obviously, they are there, but we are just trying to make a breakup of these energies. We will study latent heat separately, latent heat of vaporization separately, and when it comes to forming the ion, we have to study from the sodium gaseous atom to the sodium gaseous ion. We have to deal with the gaseous atom of every element, and then we will form its gaseous ion. Obviously, these energies will be there, but we are just trying to make a breakup of these energies. We will study all of these energies separately. And how separate they are? Two of these you have studied in physics, one of that you are studying in chemistry. And why do we actually need to study the breakups in order to simplify and have a better understanding of what is actually happening in the microscopic state, or the state at which solid, liquid and gases, the particles in solid, liquid and gases like atoms, molecules and ions, how they are actually behaving. So we have to go into the further depth, and we are trying to have a breakup of these energies. It is actually to make things pretty simplified and more understandable. Otherwise, if I just give you the sodium solid, if you start heating sodium solid, it will ultimately convert into sodium plus one gaseous ion. But what stages have happened from here to here? There are a lot of stages involved. So we cannot just study all these stages combined. We have to separate these stages. From sodium solid to liquid, that is melting, we have studied it separately. From liquid to gas, it is boiling, we have studied it separately. From gas to gaseous ion, we are going to study it now. So ionization energy it is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous positive ions. Right? If I need to write this in the equation form, let's first take an example of a sodium atom, but we have to start from the gaseous sodium atom. How does heating cause it to form an ion? Vedha is asking, how can heat just remove the electron? Because any atom's nucleus is positively charged, it is holding the electron. If we're going to start heating these electrons, what happens? That these electrons will gain more kinetic energy, and finally they will overcome the nuclear force of attraction and they will move away. If the nucleus is holding up the electrons, we just have to heat it. It will start vibrating more vigorously, and a time will come and it will start moving away. And the electron, which is actually at the highest energy level, will be the first one to remove. But if we keep on heating the sodium atom, what will happen to it? Let's say if we started heating a gaseous sodium atom, it will form a gaseous positive 1 ion. And we have removed 1 mole of electron. These state symbols are very important. It is in the gas state. You have to mention it. If you miss to write the gaseous state symbol, then it would deduct your marks. Right? So if we just keep on heating it, now what will happen? Once the gaseous sodium atom is formed, if we keep on heating it, another 1 mole of electron will be removed and it will form Na2 positive gaseous ion. But if we just keep on heating it further, what will happen? Another 1 mole of electron will be lost. And we will get Na3 positive gaseous ion. And this will keep on happening until or unless we have removed all the electrons from the sodium atom. And the sodium atom will be finally left with its nucleus only. So there are 11 electrons in the sodium atom. If you keep on removing electron one by one, and you do not have to decide which electron will be lost first. If you start heating it, the electron which is in the outermost shell, or electron which is at the highest energy, will be the first one to be removed. If you continue heating it, the electron which is at the lower energy than the outermost electron will be the second one to be removed. So these electrons will be removed as per the energy order. The electron with the highest energy will be the first one to be removed. The electron with the second last energy will be the second one to be removed. And how will you know which electron is of the highest energy? By the electronic configuration. You have already made the electronic configuration of sodium, right? 1s2, 2s2, 2p6, 3s1. So the electron in the highest energy orbital is of the highest energy. If you see the electrons of the 2px, So 2p subshell has three orbitals, 2px, 2py, and 2pz. When you have filled 2p subshell of sodium, how you have filled it? You have put one electron in the 2px, then in 2py, and then in 2pz. Once you are done filling all the orbitals of this p subshell, then you restarted filling from left to right. 1, 2, 3. So that's how you have filled total of 6 electrons in 2p of the sodium. So which electron is filled in the last in, let's say if you have already removed one electron from the sodium atom, the electron is the first one to be removed should be from the 3s. You are done with this 3s, you have removed it. Now, what you are left with is, you are left with these number of electrons. You are left with this. Now, if you have to remove one more electron from this sodium plus 1 ion, which electron would be the first one to be removed? The electron which is filled in the last. Let me write it down for you. Electron filled in last is first one to be removed. And if you just start adding these electrons, 1, 2, 3, 4, 5, 6. So this is the electron which is filled in the last in the p subshell. So this electron of 2pz will be removed first. I mean, when you are trying to remove the second electron from the sodium ion, 2pz's electron will be removed first. And after that, let's say if you have formed Na2 positive gaseous sign, which electron will now going to be removed? See, that's how you have added it. 1, 2, 3, 4, 5, 6. So this electron was removed from the p subshell first. Then after that, this is the electron which was filled, so it has to be removed. So if you have to form Na2 positive ion, this is the electron which will be removed, like this. And when you have to form Na3 positive ion, so which electron will be removed? This electron from 2px, like this. You getting my point? Now this electron will be removed to form Na3 positive ion. Rayan, Faik, Sarah. Okay. Sarah and Faik, do you guys have any confusion in it? Because it is the tough one. Now the concept will get a bit tougher. If you need me to repeat it, Sarah and Faik, you have to tell me. No means you don't want me to repeat it, or you haven't got the point. Got it. What about you, Faik? You understood it as well. Okay. So tomorrow in coming class, we will be done with a good portion of this chapter. So yes, tomorrow's coming class, which will be on Friday, we will start our past paper questions. So I'm expecting that you have to revise everything that we have studied so far. Okay. Yes, I will send you the PDF, and I'll make sure everything is uploaded on the portals, the recorded lectures and the PDF as well. In fact, I'm just doing it right now. As you will say, won't do it. I'm just doing it right now. Okay.